Today, we're diving into Data Center MVAC systems with Advanced Module 07, focusing on pressurization, makeup, degassing, and closed-loop water integrity. The goal here is to keep both the facility's chilled water and technology cooling loops full, air-controlled, clean, and pressure-stable through all operating states, whether normal, maintenance, or failure. Key areas include pressure control, qualified makeup water, air and gas removal, managing dirt and magnetite, maintaining proper water chemistry, and ensuring overall system resilience. Each of these elements plays a vital role in maintaining an efficient and reliable cooling system for data centers. This module focuses on pressurization, degassing, and water integrity within data center MVAC systems. Our goal is to engineer pressure, gas, solids, and makeup as a single controlled closed-loop service. The purpose here is to maintain positive pressure at the highest active point, absorb thermal expansion, remove free and dissolved gases, and control solids and makeup effectively. By the end of this training, you'll be able to calculate the pressure envelope and usable acceptance, select the right PMD equipment, define measurable capabilities, and demonstrate failure and restoration states. This module is designed for owners, operators, engineers from mechanical, water treatment, and controls disciplines, commissioning authorities, as well as OEM and service teams. We'll cover key concepts such as brake tanks, pressure maintenance, vacuum degassing, and dirt or magnetite control, all grounded in solid design, capability, and operating bases to ensure system integrity and performance. Here, we focus on the risk lens and decision hierarchy critical to managing the MVAC system. Safety is paramount, along with maintaining the pressure envelope. This means ensuring positive top point pressure, adequate pump suction and NPSH, appropriate component pressure and temperature ratings, independent high-pressure protection, and safe relief discharge mechanisms. Next, we emphasize continuity and maintainability, which involve isolating individual assets without compromising the system, preserving usable expansion volume, ensuring local controllers can operate independently, and managing controlled contingency refills. Finally, water integrity and evidence are vital. This includes preventing oxygen and debris from entering, qualifying fill chemistry, metering every liter added, monitoring pressure, level, gas removal, and quality trends, and conclusively addressing every failure with documented proof. These integrated factors together maintain a safe and reliable MVAC system environment. In this module, we're focusing on pressurization, degassing, and water integrity within data center MVAC systems. The learning route here takes us from intent all the way to operating proof, demonstrating how a single engineering chain can convert system physics and resilience outcomes into repeatable field evidence. We'll explore key concepts like static head, cold fill pressure, expansion volume, and relief margin, which are crucial for ensuring stable pressure conditions. Additionally, we will cover architecture elements such as pressure maintenance methods, loop separation, and qualified makeup. Finally, verification steps include using calibrated instruments, timing responses, and gathering gas and particle evidence to prove the system's proper function and its ability to recover from failures. This comprehensive approach ensures we maintain system integrity from design through operation. In this module, we focus on pressurization, degassing, and water integrity within data center MVAC systems. By the end of this training, you'll be able to design, specify, commission, and operate a complete pressure maintenance and loop integrity system. You'll gain design competence, including defining hydraulic and ownership boundaries, selecting the right pressure maintenance and degassing architectures, and reviewing maintainability. On the calculation side, you'll learn to calculate static pressure and thermal expansion, apply absolute pressure for gas law verifications, and understand margins, uncertainties, and OEM correction factors. Control-wise, you'll develop skills to sequence operations locally, issue alarms before thermal loss occurs, challenge potential failures, and restore verified readiness to the system. Understanding key terms like pressure transmitters, cooling distribution units, and sequence of events will also be essential as we move forward. This comprehensive approach ensures systems remain reliable and efficient under all conditions. This module, titled Pressurization, Degassing, and Water Integrity, covers an extensive and detailed agenda designed to guide you through the entire workstream, from the initial design basis all the way to independent failure analysis and restoration proof. We'll start by exploring the physics and architecture of the system, focusing on key concepts like the pressure envelope, expansion acceptance, and the distinctions between fixed, pump, and compressor-controlled systems, along with how facility and D2C or CDU loops are separated. Moving on, we will delve into makeup water, gas, and solids management, addressing critical topics such as source qualification and air gap, vacuum degassing, air vents and separators, magnetic dirt separation, as well as filtration and drainage methods. Then, we'll examine water chemistry and control capabilities, including decisions around chemistry and EDI, glycol blending strategies, instrumentation, BACnet and SC boundaries, and how owner performance targets and alarm systems fit into the picture. Finally, our discussion wraps up with resilience, commissioning, and operations, covering tier and rated outcomes, common mode reviews, commissioning levels 1 through 5, and the essential processes of acceptance, standard and emergency operating procedures, maintenance, laboratories, and handover. Understanding these components will give you a comprehensive framework for managing MVAC systems effectively. In this module, we focus on pressurization, degassing, and water integrity within data center MVAC systems. A key principle here is that every connection must have a clearly assigned owner, along with defined normal operating states, signals to monitor, acceptance criteria, and restoration rules. Looking at the facility chilled water loop, it includes components like chilled water headers, pumps, coils, and plate heat exchangers. Important aspects such as the plant pressure point, expansion and relief mechanisms, water chemistry, and makeup and degassing services are all critical to maintain system integrity. On the other hand, the technology cooling loop involves the CDU's secondary loop that connects to racks and cold plates. We must consider vendor-specific limits on pressure, temperature, materials, and fluids, as well as leak detection, dew point control, and follow a separate fill and service procedure to ensure reliability. At the interface level, the plate heat exchanger and the CDU serve as hydraulic separation points, preventing uncontrolled mix or crossfill. Local controls take responsibility for protection, while supervisory systems like BMS or DCM monitor governed system states. Finally, the commissioning authority maintains the acceptance records to verify compliance and performance. This module focuses on pressurization, degassing, and water integrity within data center MVAC systems. One key point here is understanding the standards architecture. Each document serves a specific purpose and must be applied correctly to the right question. It's important to recognize that a standard outcome, an engineering guide, an OEM capability, and an owner target are distinct and not interchangeable concepts. When we talk about availability outcomes, Uptime Tier 3 requires systems to be concurrently maintainable, whereas Tier 4 demands fault-tolerant and continuous cooling capabilities. Similarly, the TIA rated 3 and rated 4 classifications emphasize maintainability and fault behavior across data center infrastructure. On the engineering basis, various standards come into play. ASHRA 90.4 covers data center energy and water scope. TC 9.9 provides environmental and loop guidance for liquid cooling, and standards like EN 12828, VDI, and BSRI address pressure, water, and cleaning practices in detail. For project acceptance, the owner is responsible for declaring pressure bands, alarm latency, response, quality, and autonomy requirements. The OEM guarantees the chosen model, the designer resolves system interfaces, and commissioning confirms the installed system meets all capabilities. Finally, a quick note on terminology. PT stands for pressure transmitter, CDU for cooling distribution unit, SW for sequence of events, and OEM for original equipment manufacturer. Understanding these terms helps clarify communication throughout the project lifecycle. This module focuses on the critical importance of engineering pressure, gas, solids, and makeup together in a data center MVAC system. It's key to understand that the same symptom can arise from multiple causes, so controlling makeup alone is never a substitute for proper diagnosis. For each issue, we look at the mechanism behind it, the physical effects observed, the early warning signs, and the appropriate engineering response. For example, low top point pressure can lead to air ingress and cavitation, indicated by noise or pressure gauge readings, and is addressed by raising the fill basis or fixing leaks. Similarly, wrong precharge causes pressure swings, detected through temperature and pressure tests, which require draining the water side and setting the correct precharge. Dissolved gas can create microbubbles and corrosion, signaled by gas symptoms and managed through degassing cycles and preventing ingress. Other common problems include construction debris blocking valves, magnetite causing wear and fouling, and passing makeup valves leading to dilution and oxygen entry. Each has specific diagnostic signs and targeted responses, like filtration, magnetic separation, and fail-closed isolation valves. Chemistry mismatches result in corrosion or elastomer damage, monitored through pH and conductivity trends and controlled with appropriate treatment plans. Loop cross-contamination is identified by fluid analysis and pressure behavior, requiring hydraulic separation and dedicated service authority. Finally, the diagnosis gate process involves stabilizing safely, verifying actual pressure, correlating all related factors, correcting one cause at a time, and then retesting to restore full system authority. This comprehensive approach ensures system integrity and performance. Now we're looking at Module 07, focusing on pressurization, degassing, and water integrity in data center MVAC systems. Here we have a real piece of equipment, a pump-controlled pressure maintenance unit. This device is essential for sealed heating and chilled water circuits. Its control system works by having the pump add water when needed, while the overflow valve removes excess water to maintain balance. One standout feature is its precise capability, with a pressure tolerance of plus or minus 0.2 bar for this model. To ensure reliability, it provides continuous proof through monitoring pressure trends, the state of the pump and valve, and failure recovery processes. When selecting a unit like this, it's important to consider the pressure range, system volume, temperature, glycol content, power supply, redundancy, interfaces, and verified installed performance to make sure you get the right fit for your system. This slide focuses on the diaphragm expansion vessel, a key component in the pressurization and degassing system of a data center's MVAC system. The nominal volume of the vessel is different from the usable acceptance volume, which is important to keep in mind when planning system capacity. The membrane inside the vessel separates the system water from the gas space, ensuring proper operation and preventing contamination. Monitoring features often include level sensing and an optional rupture detector for safety. Maintenance is made easier through lockable isolation valves, drainage points, and lifting routes for safe handling. Always refer to the manufacturer's specifications for useful volume, pressure and temperature ratings, diaphragm compatibility, vessel grouping, rupture detection options, and safe replacement procedures. This ensures reliable and safe operation within your system. In this module, we focus on the side-stream vacuum-degassing, a crucial component in maintaining water integrity in data center MVAC systems. The process begins with the withdrawal of a small, controlled side stream of fluid. This fluid then undergoes degassing, where pressure is reduced to release dissolved gases. After degassing, the undersaturated fluid is returned back into the main loop, helping to maintain system stability. It's important to verify that the equipment is functioning properly by checking working pressure, vacuum levels, cycle operation, and vent paths. The image here represents a typical manufacturer's Degasser, and when setting up, we need to match the system pressure, fluid volume, temperature, glycol concentration, side stream flow, and control settings. Additionally, specifying gas performance targets with the relevant gas species and test methods ensures optimal operation. This module focuses on pressurization, degassing, and water integrity in data center MVAC systems. Here, we're looking at a real piece of equipment, the magnetic dirt and magnetite separator. Typically, this device is located before sensitive plant equipment to protect it effectively. It works through a combination of low-velocity separation and magnetic attraction to remove particles. As an example, it can capture particles as small as 5 microns at the specified flow rates. During service, solids can be drained while the system is in operation, but only where permitted. Keep in mind, this is a representative manufacturer's photograph, and it's important not to assume universal performance claims without verifying flow rates, particle sizes, pressure drops, and discharge procedures. On this slide, we're focusing on the critical step of selecting the pressure maintenance architecture before choosing any equipment for a data center MVAC system. The key factors to consider are the static height, acceptance volume, failure behavior, and how you plan to handle concurrent maintenance. There are three main architectures to keep in mind. First, fixed precharged vessels are passive and don't rely on power, making them simple but potentially large in volume. The precharge discipline is absolutely critical here, and grouping vessels so you can isolate them for maintenance is necessary. Next, pump-controlled units use an unpressurized membrane vessel, where a pump adds fluid and overflow removes it. This setup allows for a tight operating band, but it also depends heavily on power, sensors, and controls, so it's important to review those dependencies. Finally, compressor-controlled vessels regulate pressure on the gas side, offering a more flexible operating band. However, you have to carefully consider maintenance on both the pressure vessel and compressor, as well as issues like condensate management, air quality, and fail-safe behavior. Understanding these options and the abbreviations like PT for pressure transmitter and CDU for cooling distribution unit will help make informed choices that ensure system reliability and performance. In this module, we're focusing on pressurization, degassing, and water integrity within Data Center MVAC systems. It's essential to understand that the facility chilled water and the cooling distribution unit loops have separate pressure and water specifications. The heat exchanger plays a critical role by transferring heat without transferring chemistry, pressure authority, or makeup ownership silently. On the facility water system side, we deal with a central chilled water pressure point and expansion, facility metallurgy and inhibitors, a large static height, and the PMD plant serving multiple branches only when hydraulically connected. For the technology cooling system, important factors include the CDU secondary pump and vessel, vendor-approved water or dielectric fluid, small passages requiring strict cleanliness, and leak detection with supply maintained above the dew point when needed. The interface rules are also vital. They ensure pressure class and transient checks on both sides, dedicated drains, fill and sample points, no cross-connections without approved treatment, and independent alarms, isolation, and commissioning records to maintain safety and system integrity. In this module, we focus on the critical aspects of pressurization, degassing, and water integrity within the Data Center MVAC system. Before selecting any equipment, it's essential to establish a solid foundation by freezing key design criteria and controlled input parameters. This includes understanding the hydraulic and fluid characteristics, ensuring safety and resilience, and gathering evidence to support decisions. We start by analyzing the system and fluid properties, such as the volume connected by phase, the type and concentration of water glycol mixtures, and detailed temperature ranges from cold fill to maximum operating conditions. Knowing the fluid density and expansion characteristics is fundamental. Next, we consider pressure and safety factors. We survey static elevations, identify the highest active points, and determine pump suction minimums. We also review the pressure ratings of components, relief valve settings, discharge paths, and assess any vacuum risks to avoid system failures. Operating architecture must be clearly defined, including the points for pressure control, the different operational lineups spanning normal, maintenance, and failure conditions, and the makeup water source with its break tank. We also plan for degassing and filtration flow and ensure proper isolation and access for maintenance or emergency situations. Further, water quality is monitored and maintained to protect the system, while resilience and growth factors are incorporated to ensure long-term performance. Measurement, power, and control systems are integrated to provide reliable operation and monitoring. Finally, acceptance criteria and evidence gathering are crucial to validate system performance. Key abbreviations like PT for pressure transmitter, CDU for cooling distribution unit, SW for sequence of events, and OEM for original equipment manufacturer help streamline communication throughout this process. This slide covers the essential pressurization and expansion formulas used in data center MVAC systems. First, we have the static head calculation, which determines pressure changes due to elevation differences, with water pressure approximated at 0.0981 bar per meter. Next, the cold fill minimum pressure needs to maintain an approved positive value at the highest active point to ensure system integrity. Top point pressure is then calculated by subtracting the static head from the plant pressure, and it's vital to check this across all operating states, including cold, warm, pump-on, and standby. Expansion volume accounts for density changes between cold and hot water, requiring accurate fluid data through the temperature range. The acceptance factor simplifies the fixed vessel sizing by converting gauge pressure to absolute pressure. Using this factor, we determine the nominal vessel size and then apply additional factors like reserve capacity and OEM specifications. Relief margin settings protect the lowest rated components by ensuring operating pressure stays below relief thresholds to prevent unnecessary activation. Finally, Makeup Water volume monitoring helps identify leaks or faults by analyzing trends in added water over time. Overall, following these formulas ensures a robust and reliable pressurization system. Here we have a worked example focusing on a water system with a static height of 45 meters and a closed-loop expansion duty. The system volume is 280 cubic meters, with a 1% expansion across the temperature range, a 0.50 bar top point margin, an 8.5 bar maximum control pressure, and a 10 bar relief setting. First, we calculate the static head by multiplying the height by the pressure factor, which gives us 4.41 bar. Adding the top point margin of 0.50 bar results in a minimum gauge pressure of 4.91 bar. Next, the expansion volume is found by taking 1% of the total system volume, which equals 2.80 cubic meters. The absolute pressure band ranges from 5.92 to 9.51 bar absolute, representing the pressure limits within which the system operates safely. To size the expansion vessel, we use a vessel sizing factor of 37.7%. Dividing the expansion volume by this factor gives approximately 7.4 cubic meters for the screened vessel volume. Finally, when selecting the training vessel, we start near 8 cubic meters nominal capacity, then factor in reserve capacity, initial fill, redundancy, vessel grouping, pressure class, temperature, glycol content, and the exact OEM method to ensure optimal performance and safety. Here we focus on the expansion vessel, which plays a critical role in managing the pressure within the MVAC system. The gas cushion inside the vessel accepts thermally expanded fluid, maintaining system stability. However, if the precharge pressure is incorrect, or if isolation valves are closed, or the membrane fails, the vessel loses its ability to accept this expansion. When selecting and maintaining an expansion vessel, several key factors must be considered. First, the pressure class, which includes the design pressure and temperature, as well as relief settings and transient pressures below rating. Next, the precharge must be set accurately, and this is done only when the water side is isolated and drained. A calibrated gas gauge is essential for this. Usable acceptance volume isn't just about nominal volume. It's important to use the absolute pressure band and follow the original equipment manufacturer's method to determine this correctly. Material compatibility is crucial, ensuring the diaphragm can handle water or glycol mixtures, inhibitors, varying temperatures, and the type of gas used. Access features are also important. The vessel should have lockable isolation valves, a drain, a gauge, a charging valve, and a clear route for lifting and replacement. Finally, resilience is key. Grouping vessels can help ensure that maintenance or failure of one does not compromise the entire system's safety margin. To summarize the operating states, in the cold state, the gas volume is high and water volume is low. As the system warms, water expands, compressing the gas, which leads to a rise in system pressure. Understanding this dynamic is essential for proper vessel function and system integrity. On this slide, we're focusing on a worked example of the usable expansion acceptance screen for a data center MVAC system. First, we look at the system volume, which is 280 cubic meters. The fluid expansion is given as 1%, leading to an expansion volume of 2.80 cubic meters. Next, we consider the absolute pressures involved, which range between 5.92 and 9.51 bar absolute. This is a critical factor for proper system design and operation. The screen acceptance is calculated at 37.7%. while the screen nominal volume is approximately 7.4 cubic meters. Importantly, we must use absolute pressures during calculations and then explain how factors like precharge, initial fill, operating temperature, glycol content, isolation, and redundancy impact the installed solution. Finally, before finalizing the selection, it's essential to recalculate using actual fluid and temperature data, apply precise OEM sizing guidelines, and consider reserves, vessel grouping, pressure class, and maintenance or failure capacities to ensure reliability and safety. In this section, we're focusing on active pressure maintenance, which is a critical process in maintaining system stability. The first step is to measure pressure accurately using a pressure transmitter and an independent gauge. Next, when the pressure drops below a certain band, a lead pump kicks in, with a standby pump ready to take over if needed. If the pressure rises above that band, a controlled overflow valve allows for a safe spill. Expansion is then managed by storing excess volume in a membrane vessel or tank. Finally, verification is done at the top pressure point, ensuring there's a relief margin for safety. This capability has been proven to work reliably across different conditions, including cold, warm, maintenance, and failure states. Remember, the specific tight pressure band is model dependent, so it's essential to verify sensor accuracy, the effective deadband, system response, cycling, standby changeover, and power recovery on the actual installed system. On this slide, we focus on the critical decision points for pressure maintenance systems in Data Center MVAC setups. The key takeaway here is to select the complete service rather than just the pump or the nominal vessel volume. This means considering the entire system's needs holistically. Under pressure and safety, we must account for cold minimum and highest point margins, warm maximum and relief margins, absolute pressure sizing, the correct pressure and temperature class, and ensure independent indication and relief discharge for safety. When it comes to capacity and performance, factors like system volume and expansion, usable acceptance, add or spill flow, deadband and cycling, Glycol correction, and considerations for initial fill and future expansion zones play vital roles. Lastly, failure and operability aspects include permitted maintenance states, strategies for lead, standby, and power loss scenarios, sensor failure handling, vessel isolation, local autonomy, as well as provisions for drains, access, lifting, and spares to ensure continuous, reliable operation. Understanding these selection gates ensures we maintain both system integrity and operational resilience. On this slide, we're focusing on expansion vessel membrane rupture detection, a critical aspect of pressurization and water integrity in MVAC systems. Rapid alarm response is essential, but the exact latency, coverage, and required actions depend on specific owner or OEM requirements and must be verified through witnessing. Key design items include the detection technology, which can be either an OEM rupture sensor or an independent liquid or gas indication. The testing involves simulating approved sensor conditions to ensure the system behaves as expected, with a project example aiming for alarms within 5 seconds. We emphasize comprehensive coverage, meaning every required vessel or bank needs to be monitored, challenging each map tag and maintaining point-to-point records. Control actions must be defined clearly, whether that's alarming, isolating, or transferring functions as approved. Functional tests protect pressure integrity while trending and responses are monitored closely. Fail-safe behaviors such as detecting open circuits, shorts, or power loss, along with fault recording and controlled maintenance bypasses, are mandatory. These bypasses should be visible, timed, and access controlled, with proper audit logs maintained. Independent confirmation through diagnostic tests based on pressure swing, pre-charge, or level is also necessary to validate system status as found and as left. Restoration processes address band and standby capacity recovery, and all restorations must be signed off. Importantly, no universal 5-second alarm clause from Uptime, TIA, or ASHRAE standards is claimed here. The acceptance of performance values hinges on the full support of product capabilities, logic, network paths, and test methods. This thorough approach ensures a reliable, responsive system for maintaining pressurization and water integrity. On this slide, we're focusing on the makeup architecture for the MVAC system, which follows a clear sequence of steps: qualify, separate, meter, condition, and add. The first step is to identify a qualified source, ensuring it can be safely used with proper release and isolation measures. Next, we protect that source from contamination by using backflow prevention or an air gap. The third step involves a break tank to regulate water levels and prevent overflow. Then, the water is treated and pumped in a metered and limited way to maintain quality. Finally, there's the closed-loop point where controlled water addition occurs to maintain system balance. Importantly, treatment is kept separate from pressure control, and automatic water addition is carefully limited by volume and time. Any repeated need for makeup water usually indicates leakage or integrity issues until proven otherwise. In this module, we focus on makeup source qualification and autonomy for data center MVAC systems. Choosing the right water source and treatment depends on several factors like the chemistry of the water, contamination risks, availability, and local regulations around backflow and discharge. For potable water, we ensure backflow protection, typically through an air gap, and acceptance requires approval from the authority having jurisdiction along with device testing. When using softened water, hardness reduction is crucial, and ongoing control involves monitoring capacity, salt, and hardness levels. Reverse osmosis and demineralized water provide low-dissolved solids, but depending on the design, we might need to remineralize or add inhibitors, all while monitoring conductivity and corrosion potential. For ultrapure water, technologies like electrodeionization are considered, backed by OEM guarantees and testing. If reclaimed or rainwater is used, this only happens after rigorous legal and contamination reviews. These sources require dedicated storage tanks, proper treatment, clear signage, risk assessment, and controlled release procedures to maintain safety. Autonomy involves managing storage to match declared operating durations, with controls such as low-level alarms, overflow protections, and hygiene checks. Automatic addition mechanisms regulate normal loss quantities, monitoring rate, duration, counts, and total volumes against a 30-day baseline with alarms for any anomalies. It's important to note that the Uptime Institute's public makeup water guidelines primarily address evaporative cooling tower demands, which differ from the closed-loop refill needs we cover here. This distinction ensures that system design and maintenance are appropriately tailored to the specific water management requirements of data center MVAC systems. Now, let's dive into the process of vacuum degassing in our data center MVAC system. The core idea here is that by reducing pressure, we can effectively release dissolved gases from the fluid. We start by withdrawing a small, controlled side stream from the main system. Then, we reduce the pressure using a vacuum, which lowers the gas solubility in the fluid. This causes the dissolved gases to form bubbles, which can then be vented out safely. Finally, the undersaturated fluid is returned back into the loop. It's crucial to select the process parameters carefully based on volume, working pressure, temperature, glycol content, side stream flow, and removal time. Also, always verify isolation, check the strainer, vacuum cycle, vent path, containment, and ensure everything is safely returned to service. This slide outlines the critical aspects of Degasser capability, focusing on defining the gas, the method, the condition, and the time involved. We start with the baseline, which includes sample collection and identifying symptoms. Then we move to the envelope, where we monitor pressure, temperature, and glycol levels. Next is the machine phase, tracking vacuum, flow, and cycle parameters. The system response comes after, characterized by noise levels and maintaining stable flow. Finally, acceptance criteria must be established, including target values and retained records for verification. Keep in mind, a target such as less than 0.1 milligrams per liter of dissolved gas is not universal. It's essential to specify the exact gas species, test method, sampling point, temperature and pressure, uncertainty levels, completion time, and OEM guarantees. If these details aren't available, rely on functional cycle and symptom-based acceptance to ensure system integrity. On this slide, we focus on the essential air management devices used in MVAC systems and how to apply each mechanism correctly. It's important to understand that free air, microbubbles, and dissolved gas all require different devices for effective management, and a vacuum breaker serves primarily as protection, not as a degasser. Manual vents are used during the initial fill to remove trapped high-point air and must be accessible with controlled discharge to ensure no air remains and the cap is properly restored. Automatic air vents operate continuously to release free air at high points or separators, using float action to prevent leaks. Microbubble separators coalesce circulating microbubbles at designed flow and low-pressure locations, ensuring the system maintains optimal performance by proving flow, pressure differential, and proper venting. Vacuum degassers remove dissolved gases within the OEM's specified pressure and temperature ranges, relying on vacuum cycles and returns. Vacuum breakers prevent damaging subatmospheric states, but should only be installed where transient analysis demands it, with correctly set points for safe admission. For CDU vents and fill carts, adherence to vendor procedures and approved fluids is crucial, ensuring no trapped air remains and the system passes leak tests. Vent discharges must safely handle water or glycol, directing them to drains or collection points that are carefully inspected during testing. Isolation devices enable controlled servicing by being lockable and tagged for safety. Finally, lineup and restoration are complete only when circulation is stable, pressure stays within the envelope, vent paths are leak-free, and the normal system lineup is fully restored. This thorough approach ensures reliable and efficient system operation. On this slide, we focus on the critical aspects of dirt, magnetite, and filtration architecture within Data Center MVAC systems. Choosing the right filtration device depends heavily on factors such as the particle removal mechanism, the size of sensitive passages, pressure drop considerations, and ensuring safe service methods. We look at various devices, starting with flushing filters, primarily used to remove construction debris, monitored by pressure drop and sampling to confirm cleanliness goals are met. Y strainers provide coarse equipment protection and require regular inspection plus monitoring of pressure drop. Dirt separators continuously separate solids at low velocity and must be sized for the rated flow with proper drainage. Magnetic separators target ferrous particles like magnetite and demand magnet servicing along with sampling and solid records. Sidestream bags perform micron-level polishing with attention to flow rating and pressure drop, requiring particle result monitoring and timely changes. Cartridge and full flow filters protect fine passages and use bypass and terminal pressure drop limits to maintain integrity. Finally, drains and sample points are essential for removing and characterizing solids safely, ensuring representative sampling and acceptance testing. It's important to remember that product filter claims, such as 99% submicron, depend on specific flow and particle distributions and do not universally meet Uptime, TIA, or ASHRAE standards. Understanding these devices and monitoring parameters is key to maintaining system cleanliness and protecting sensitive components. In this module, we focus on closed-loop water chemistry and EDI decisions within Data Center MVAC systems. It's important to understand that chemistry here is fundamentally a materials and corrosion program. Simply aiming for the lowest conductivity doesn't automatically guarantee safety. So, we approach this through a clear engineering framework consisting of decision, engineering questions, control, and evidence. First, we analyze the water source. What exactly is entering the system? We confirm approved sources, check laboratory reports, and consider a detailed materials inventory, including metals, elastomers, and brazes. Using compatibility matrices and approved submittals helps ensure all materials work well together. Next, controlling oxygen is critical. Identifying where air or fresh water might enter allows us to maintain a closed loop with degassing and limited makeup water. We monitor trends in makeup and gas content, along with pH and conductivity, to keep the system within the correct range. Alarms, sampling frequency, and both trend data plus laboratory analysis enable ongoing control. The use of inhibitors or biocides is determined by the treatment plan, with careful dosing authority and concentration certificates, verifying proper application. Considering reverse osmosis or demineralization, we ask if lowering ionic loading actually benefits the system, and we pay close attention to storage and post-treatment processes. Product water testing, targeting an EDI conductivity range of 1 to 5 microsiemens per centimeter, is applied only if project or OEM requirements specify it. Feed quality, material compatibility, and monitoring are key to ensuring system integrity, supported by guarantees and witness testing. Should deviations occur, such as leaks or contamination, protocols for isolation, sampling, assessment, and restoration are in place, followed by disposition decisions and retesting. Finally, it's crucial to remember, do not claim a universal conductivity standard of less than 1 to 5 microsiemens per centimeter as an absolute rule from Uptime, TIA, or ASHRAE. Instead, chemistry parameters must be approved collaboratively with vendors and water treatment specialists to define the appropriate chemistry envelope for each specific application. In this module, we focus on the critical topic of glycol selection, concentration, and automatic blending in data center MVAC systems. Glycol plays a significant role as it affects density, expansion, viscosity, pump power, heat transfer, seals, and the makeup strategy. Choosing the right glycol type, whether propylene glycol, ethylene glycol, or an inhibited product, is essential and must be an approved single product with documented safety data and compatibility. When it comes to concentration, it's important to establish this on either a mass or volume basis, using tools like refractometers or density measurements, calibrated with samples. Automatic blending systems should have strict controls, including ratio limits and fail-closed features, and should be subject to timed batch tests and acoustic metering for accuracy. For design and acceptance, we must consider freeze and burst cases based on the lowest credible temperatures, ensure calculations and data support system sizing, and master hydraulic and expansion corrections. Ongoing monitoring includes accounting for added water, keeping ratios balanced, and verifying through independent sampling. Finally, automatic blending should only be accepted when the source quality, ratio accuracy, fail-safe behavior, maintenance bypass, and independent sample verification have all been proven reliable. This comprehensive approach ensures optimal system performance and longevity. In this module, we focus on the critical relationship between Uptime tier and TIA rated outcomes and how those translate directly into pressure system behaviors. Public standards set the expectations for infrastructure performance, but the real challenge is translating these outcomes into practical elements like PMD capacity, system topology, controls, and rigorous testing. For Tier 3 or Rated 3 systems, the key requirement is concurrent maintenance of permitted components and distribution paths. This means you can isolate and maintain any specific unit, vessel bank, instrument, or treatment component without losing the essential cooling environment. Moving to Tier 4 or Rated 4, the infrastructure must be fault-tolerant and support continuous cooling performance even in the event of a failure. This requires that a single fault cannot disrupt pressure, makeup water, chemistry, or cooling beyond safe operating limits. A core part of the project declaration is to clearly define the retained pressure envelope, allowable degradation limits, alarm and response protocols, stored acceptance criteria, makeup autonomy, and restoration processes. Equally important is proving that the system can handle one failure at a time under realistic thermal and hydraulic conditions. Finally, you'll often encounter abbreviations like PT for pressure transmitter, CDU for cooling distribution unit, SW for sequence of events, and OEM for original equipment manufacturer. Knowing these helps in understanding system components and their roles in maintaining water integrity and pressurization. On this slide, we're focusing on the Advanced PMD Capability Matrix, which covers requirement, qualification, and proof for the MVAC system in data centers. It's crucial to use aggressive values only when the selected architecture and manufacturer can guarantee them under the declared system conditions. For example, pressure stability targets might be around plus or minus 0.1 to 0.2 bar. This involves calibrated trends across load and failure scenarios to ensure reliability. For vacuum-degassing, targets depend on specific gas species and methods, considering volume, pressure, temperature, glycol concentration, and timing. Magnetite removal focuses on particle size, flow, pressure drop, and magnetic separation, with before and after samples to prove effectiveness. Membrane rupture detection requires fast alarms and fail-safe sensor coverage tested repeatedly with a common clock approach. Inline EDI conductivity targets, such as 1 to 5 microsiemens per centimeter, apply only if they're approved based on feed water quality, materials, and treatment plans. Multi-source makeup water is managed automatically, but only through qualified routes ensuring proper air gaps, tanks, metering, and autonomous controls. The system employs N+1 active PMDs to avoid common mode single faults across pumps, vessels, power supplies, sensors, and controllers. Maintenance and fault scenarios are carefully planned, and the network relies on a secure Ethernet ring with BACnet/SC protocol, declared latency, and robust TLS/PKI with local autonomy and topology controls. Network loss, recovery, and sequence of events logging are all managed to meet rigorous standards gates, which include Uptime and TIA outcomes, ASHRAE engineering scopes, owner acceptance, OEM guarantees, and installed commissioning evidence. This comprehensive matrix ensures the system operates safely, efficiently, and in line with all critical performance demands. Here, We have an instrumentation architecture designed to ensure every critical value has an independent proof. This means each vital measurement is verified separately to guarantee accuracy and reliability. We use quality flags, calibrated references, and common timestamps to maintain data integrity. Higher-level systems receive governed states to oversee overall operations, while local control focuses on equipment protection. For instance, sensors like PT01 track plant pressure, PI01 serves as a calibrated gauge, PT02 monitors the highest point pressure, and LT01 measures brake tank levels. Flow rates and safety measures are also closely monitored through devices like FM01 for makeup flow, PSH01 for relief discharge proof, and DG01 for vacuum, cycle, and fault status. WQ01 checks conductivity alongside sampling. At the core, the local PMD controller manages pressure bands, staging, limits, and alarms to maintain safe operating envelopes. It ensures that even if there's a failure in the higher-level network or supervisory system, the control boundary is maintained locally to keep pressure under safe control. Monitoring, alarms, and limits are supported by systems like BMS and DCM, and all data is recorded and verified through commissioning records to ensure continuous calibration, synchronized trending, testing, and restoration efforts. Here we focus on controls and cybersecurity, achieving secure communication without compromising local safety. BACnet Secure Connect ensures encrypted, mutually authenticated communication, but it importantly does not impose a strict 50 millisecond ring recovery requirement, nor does it replace deterministic local control. Local logic plays a crucial role, with pressure and safety systems operating independently. Dual pressure transmitters and gauges provide independent proof, while a common SOE clock timestamps events consistently. Security features include BACnet/SC using TLS and PKI for encryption and authentication, combined with role-based access to enforce least privilege. Configuration backups allow for approved restores, and continuous network health monitoring checks paths and certificates. Supervision by BMS or DCM systems governs the overall network, but local autonomy is key. Network loss should never prevent pressure protection, lead or standby transfers, or hardwired safety actions. If project latency under 50 milliseconds is necessary, we must define endpoints, load, topology, and performance percentiles carefully. Testing is critical, breaking each path to prove control continuity, alarm delivery, sequence of events, and secure restoration. Finally, maintaining a clear security boundary ensures that certificate expiry, switch failure, or BMS outage never become hidden, common mode points of failure that could affect critical cooling systems. This module covers the critical operating sequence for pressurization, degassing, and water integrity in the Data Center MVAC system. The process involves 6 key steps: qualify, fill, pressurize, degass, limit makeup, and restore. First, we qualify by ensuring released water is properly handled, the air gap and backflow protection are healthy, and the approved lineup is verified. Next, we fill the tank, monitoring the level band, confirming the overflow is clear, and activating low-low protection to avoid risks. During pressurization, the lead pump operates within the cold band, maintaining a top point margin, and standby pumps are ready to take over if needed. Then comes degassing, which uses a side stream vacuum or vent system, while keeping return pressure within acceptable limits. Makeup water is carefully limited through metered volume over time, with alarms for recurring refills. It's crucial never to mask leaks during this phase. Finally, we restore the system by removing overrides, proving pressure and relief margin, and closing any evidence of anomalies. Local protection always controls pressure and equipment limits, while BMS or DCM systems can only optimize within those approved boundaries. In case of failures, there are defined responses. For a pressure transmitter failure, the system will fall back, stop unsafe actions, and alarm. If the lead pump fails, standby pumps start and recovery is proven. Low-low tank levels inhibit pumps to prevent dry running, and during power loss, stored pressure ensures a controlled restart. Manual refill is a controlled operation requiring authorization, precise metering, pressure observation, leak checking, and then restoration of automatic system control to maintain water integrity and system safety. This slide covers the alarm philosophy for maintaining pressure integrity in the Data Center MVAC system. The key idea is to detect loss of pressure integrity before it affects thermal duty. Each alarm is designed with a clear structure. It needs a physical trigger, an automatic action, an operator response, a reset condition, and a documented closeout record. We prioritize alarms from P1 to P3. For example, a P1 alarm like low-pressure triggers, starting a standby system to prevent unsafe conditions, and the operator must verify pressure and locate any leaks. High-pressure alarms, also P1, stop filling and check thermal states to restore relief margin. P2 alarms include excess makeup water rate or low break tank levels, with automatic stops to protect equipment and operator checks to verify supply and levels. Degasser faults, also P2, involve isolating the cycle and troubleshooting components. P3 alarms focus on chemistry or solids deviations, prompting sampling and contamination assessment before approval. The alarm chain flows from detection, validation, and protection through response, verification of normal conditions, and formal reset and documentation, ensuring the system remains reliable and safe. On this slide, we focus on the failure modes and effects analysis, or FMEA, specifically for the pressurization, degassing, and water integrity in data center MVAC systems. It's crucial to understand that silent pressure failures often turn into thermal failures at the highest point of the system. Each failure mode listed here, from lead PM pump trips to power or common mode issues, impacts physical system effects like pressure decay or gas migration. We detect these failures using methods such as pressure trend monitoring, sensor alarms, and communication quality checks. Importantly, the automatic or operator responses are designed to preserve system pressure, maintain water quality, and ensure safe restoration. For example, standby pumps are started upon lead pump failure, or faulty valves are isolated and repaired. Lastly, note the common mode hold point warning. Never claim N+1 redundancy if there's a shared untested dependency among vessels, sensors, power, or other critical components. This ensures we don't overlook systemic vulnerabilities that could lead to failure. Here, we focus on building a truly resilient pressurization system by removing single points of dependency while maintaining the safe pressure envelope. It's important to understand that simply having capacity redundancy isn't enough unless all common dependencies, like water supply, power, control systems, piping, vessels, and restoration processes, are independently verified and proven reliable. We do this by addressing each key component. For vessels, we split them into banks with isolation capabilities to retain acceptance. Pumps operate on a duty and standby basis, equipped with check and isolation valves to prevent failure propagation. Power must come from an approved source with automatic restart and stored pressure backup to handle interruptions. Control systems include local protection and independent pressure proofing to ensure continuous operation. Makeup water is tightly controlled with metered sources, air gaps for safety, and contingency planning. Degassing and filtering units are designed to be isolatable without compromising system pressure. Finally, the Integrated System Test Challenge follows a strict order, starting from sensors and moving through lead pumps, power and control, makeup supply, vessel banks, degassers, and restoration. By changing one dependency at a time and using synchronized evidence, we can confidently prove resilience at every step. This slide covers commissioning levels 1 through 3 for the Data Center MVAC system, focusing on pressurization, degassing, and water integrity. At level 1, we verify the design and factory build by reviewing the owner's project requirements and basis of design, along with calculations, PNID diagrams, product ratings, and factory acceptance tests for controllers, pumps, vessels, and degassers. Moving to level 2, the focus is on installation checks, ensuring all tags and orientation are correct, isolation and drain points are in place, precharge and lifting access are verified, and sensor locations and terminations are properly handled. Then, at level 3, we start up and conduct site acceptance testing, confirming the system is clean, filled, and vented, checking rotation and safety functions, performing point-to-point tests, calibrations, initial tuning, and finally water quality release. The critical point here is that these commissioning levels ensure the system's design, installation, and operational readiness before functional performance testing. Alongside these, we have evidence gates like controlled inputs, approved products, installed conditions, calibrated records, and visibility of any open defects, all crucial for thorough verification. This slide covers the commissioning proof chain from calculation all the way through to integrated restoration in the MVAC system. It's important to understand that acceptance is cumulative. If we skip any early level, that missed step becomes an unresolved risk later during the high-level testing and integrated system testing. At level 1, we focus on the design, looking at volume, elevation, pressure envelopes, PNIDs, and cause and effect. Level 2 moves to factory aspects, including logic, pumps, vessels, degassers, and factory acceptance tests with certificates. Installation is covered at level 3, where we handle lineup, tagging, pre-charge, calibration, air gaps, and drains. Functional testing at level 4 involves fine-tuning deadbands, makeup limits, degassing, filtering, and alarms. Finally, level 5 includes the HLT and IST, monitoring sensors, pumps, power loss, leaks, relief valves, and restoring normal system states. Supporting these levels are detailed calculations of volume, expansion, static height, and absolute pressure, along with product ratings, acceptance, and certificates. Field activities like pre-charge, calibration, top pressure, and metering tie everything together before thorough testing through SAT, HLT, and IST, followed by closeout procedures that ensure all defects are resolved, documents indexed, lineups normalized, and operators fully trained to respond effectively. This comprehensive process ensures the system's integrity and reliability from start to finish. On this slide, we're focusing on the overall PMD acceptance criteria for the Data Center MVAC system. Each criterion here is backed by a numeric or observable basis, a repeatable test method, and retained evidence to ensure reliability. Starting with cold pressure, the pass/fail basis is an approved band or top margin, measured with calibrated pressure transmitters and gauges, with trends and calibration records kept as evidence. For warm maximum pressure, it must stay below the relief margin, tested through thermal or simulated demand methods, again supported by trend data and system settings. Expansion criteria rely on confirming usable volume availability via pre-charge and bank isolation, using calculations and OEM data for validation. Makeup water must be metered to ensure no passing and stay within limits. Timed fill and closure methods verify this, with volume and event trends documented. Degassing is proven through vacuum cycles and vent cycles, with functional cycles logged for reference. Solids are checked for cleanliness and differential pressure targets through sampling and inspection, with reports capturing solids retained. We maintain chemistry within an approved water and glycol envelope, using representative samples and lab reports as evidence. Restoration is confirmed by normal lineup and standby readiness, with failure and recovery documented via signed IST forms. Importantly, any failure remains open until its cause, correction, retesting, evidence, and restoration to normal state are all approved, ensuring complete system integrity before acceptance. Now let's focus on degassing and filtration commissioning, a critical step in ensuring the integrity of the Data Center MVAC system. The key here is to prove the complete hydraulic path and result, not just that the equipment powers on. We start with verifying isolation and bypass by confirming approved normal and service positions, followed by a detailed walk-down and valve challenge with tagged lineups. For strainers and filters, we check cleanliness and ensure the differential pressure is within limits, inspecting and trending conditions as they are found and left. Next, sidestream flow must fall inside the OEM's specified range, which we balance and verify, carefully recording the flow data. Achieving declared vacuum levels requires repeated cycles with trending to monitor progress. Venting and draining need to be safe, providing an open route without leakage, and this is observed during operation. Inspection includes evaluating particle results to confirm that project targets have been reached based on approved sampling methods. All findings are documented in a comprehensive report. In case of failure, faults are detected and pressure services are protected, with systematic challenges to pumps, valves, and sensors following the sequence of events. Restoration is confirmed by achieving an automatic state-stable condition and running recovery tests, all recorded with signed documentation. Remember, any gas or particle claims made without a clear system condition, defined test methods, and retained results remain unverified and cannot be accepted. This structured approach ensures we maintain water integrity and system reliability throughout commissioning. In this module on pressurization, degassing, and water integrity, we're focusing on the critical steps for water chemistry and glycol commissioning in data center MVAC systems. Before releasing the loop, it's essential that the source water, materials, treatment processes, sampling, and operating limits all align perfectly. We approach this by thoroughly checking the source water against approved source limits using pre-fill samples backed by laboratory reports. Then we flush and clean the system to meet specified cleanliness levels, verified through samples, visual inspections, and differential pressure readings documented in cleaning reports. Next, pH and conductivity must fall within an approved range, validated by calibrated field and lab instruments with trending reports. Inhibitors and glycol concentrations require strict adherence to supplier methods and certificates, with quality confirmed through refractometer readings and sample records. For water treatment units like EDI and RO, the product quality declared must be maintained by running at design feed conditions, monitored through trends and samples. During makeup events, we ensure no unacceptable dilution occurs by timed additions, resampling, and using mass balance calculations. Ultimately, all acceptance limits are derived from approved materials and the water treatment program specific to the system, not from generic ultrapure water targets. Establishing a stable baseline register after circulation is key to maintaining these standards and ensuring system integrity throughout operation. This slide covers the operating procedure for controlled cold fill and return to automatic service in a data center MVAC system. First, it's crucial to assign a local authority who will oversee the process and ensure every added liter is metered. You must prove the highest point in the system and only remove overrides after a stable observation period to guarantee system integrity. The procedure breaks down into 6 clear steps. Step 1 is declaring the permit and authority along with an approved lineup and releasing water as needed. Step 2 involves preparation, checking the air gap, vents, drains, and precharging the system. Next, step 3 is a slow, controlled fill while venting high points and recording meter readings. Step 4 is pressurization, where you confirm the lead and standby systems, prove the top point, and check relief valves. Step 5 focuses on degassing and filtering by proving flow and vacuum, venting and draining, and trending cycles. Finally, step 6 restores the system by removing overrides, engaging automatic protection, and closing with proper evidence. The slide also emphasizes fault path protocols. If any fault occurs, stop water addition immediately, maintain safe pressure, validate the pressure transmitter or gauge, isolate the failed section, activate authorized standby or contingency plans, escalate the issue, and keep detailed records. Importantly, never allow unmetered fill. Every addition must be quantified. Avoid blind resets by proving the cause and actual pressure first. Ensure no relief risk by verifying margin and discharge parameters, and never perform a false closeout. Always restore the lineup and maintain authorized control. This process ensures safe, reliable operation and protects the system from damage. In this module, we focus on maintaining the MVAC system's pressurization, degassing, and water integrity to ensure safe and reliable operation. Maintenance tasks are critical. They protect the acceptance volume, ensure measurement integrity, and allow for safe recovery after interventions. Before closing any work, it's essential that safe isolation is confirmed, calibration proofs are completed, functional tests are conducted, and all restorations are well documented. Key areas include vessels and precharge, where we isolate and drain the water side, apply calibrated gas pressure, and monitor membrane or rupture sensors. For pumps and valves, we perform lead and standby tests, check isolation valves, and protect against dry runs and leaks. Degassers and filters involve managing strainers, vacuum conditions, vents, cycling, differential pressure monitoring, and ensuring safe discharge of solids. Instrumentation requires careful calibration of pressure transmitters, gauges, level meters, and the use of quality flags, timestamps, and sequence of events logging. Water path management focuses on maintaining air gaps, tank hygiene, overflow and drainage controls, and collecting source and loop samples. Finally, relief and safety devices must have proper settings, valid certification, secure discharge routes, operational switches, as well as accessible and safe lifting arrangements. The return to service gate confirms that guards and caps are restored, drains are closed, valves are approved, isolation is removed, standby units are available, Alarms are reset by authorized personnel, and all evidence is carefully indexed. This thorough process ensures the MVAC system remains safe, functional, and reliable. On this slide, we're focusing on troubleshooting pressurization issues by following a clear, step-by-step process from symptom to physical cause. First, stabilize the system to retain safe pressure levels, protect pumps and coils, and start any approved standby equipment. Next, verify actual conditions by comparing gauge readings, pressure transmitter data, and the highest point pressure, while also checking the relief and tank states. Then, check the makeup water by monitoring meter volume over time, ensuring valves aren't passing unnecessarily, and inspecting tanks and overflow systems. After that, check acceptance factors like pre-charge, isolation integrity, membrane condition, and thermal state to identify any anomalies. Proceed to examine gas and solids by reviewing vacuum levels, cycles, differential pressure, vents, strainers, and potential air leaks. Finally, prove recovery by confirming a stable pressure band, maintaining the correct top margin, establishing a normal makeup baseline, and restoring full operational authority. And remember the critical hold point. Stop any troubleshooting if pressure, relief path, or water quality is uncertain. This method creates a solid evidence chain from the initial state through diagnosis, correction, and retesting to fully restore system normalcy. When dealing with emergency operating response, life safety and thermal stabilization always come first, followed by preserving evidence and restoring systems deliberately. In a low-pressure or active leak scenario, it's critical to protect pump suction and maintain cooling flow. Verify the actual pressure, isolate the smallest safe domain, and start any approved standby systems. Importantly, avoid hiding the leak with unrestricted fill. For high-pressure or relief situations, stop makeup and PM pumps as designed. Verify the thermal and isolation state, keep the discharge route safe, and inspect the relief device before returning to normal operation. When facing makeup contamination, stop the uncontrolled source, record added volume and source, sample the affected loop, assess inhibitor or glycol dilution, and authorize recovery chemistry. In cases of control or power loss, local safeties remain authoritative. Use stored vessel acceptance, transfer to an approved source, verify the restart sequence, and restore alarms, network, and normal lineup. If escalation is needed, incident authority should include mechanical, controls, and water specialists, IT load owner, safety and environmental responders, and an evidence custodian. In this practical lab, we focus on calculating and proving the cold fill pressure for a data center MVAC system. Starting with converting the elevation difference into pressure, we use the static height of 45 meters to determine a pressure of 4.41 bar. Then, by adding the required top point margin of 0.50 bar, we arrive at a total required pressure of 4.91 bar. Key field inputs include the survey elevation, fluid density, the highest active point, relief settings, and component pressure ratings. Testing involves using a calibrated plant pressure transmitter and an independent gauge at the highest point under stable cold conditions to verify accuracy. The challenge is to demonstrate system reliability in case of a plant pressure transmitter failure and lead pump shutdown, ensuring fallback and standby measures work without triggering relief. A successful pass means confirming that the top margin, control band, and maximum pressure are repeatable and properly recorded with precise tagging and timing. This approach ensures water integrity and safe system pressurization throughout the plant. Now let's dive into Practical Lab 2, where we focus on size usable expansion acceptance in the Data Center MVAC system. The key here is to use absolute pressure to understand how various factors like pre-charge, initial fill, temperature, glycol content, and redundancy impact the installed capacity of the system. We start with a system volume of 280 cubic meters and a fluid expansion rate of 1%, which gives us an expansion volume of 2.80 cubic meters. The absolute pressures here range between 5.92 and 9.51 bar absolute, and from these numbers, we calculate an acceptance of 37.7%. The screen nominal volume is approximately 7.4 cubic meters. Finally, the lab decision requires us to select the vessel grouping and isolation strategy. This step ensures that even during maintenance or fault conditions, the system maintains the required acceptance. It's crucial to recalculate using the exact fluid properties and the approved OEM method to confirm these parameters accurately. This approach guarantees system reliability and performance under varying operational scenarios. In this practical lab, we're focusing on diagnosing abnormal automatic makeup in the Data Center MVAC system. It's important to understand that a stable pressure reading alone does not prove system integrity when water is repeatedly added. Watch for repeated high-volume makeup events over 24 hours, as these signal potential issues. To troubleshoot effectively, start by verifying your meter readings against timed volumes, and check pressure transmitters against calibrated gauges. Then, correlate tank levels, relief drain activity, and pressure and temperature cycles for a fuller picture. Next, isolate the problem by checking for passing valves, vessel banks, or external leaks. Testing is crucial. Examine the precharge and membrane, as well as relief and Degasser paths. After pinpointing the issue, carry out authorized repairs and assess water quality to ensure everything is restored properly. Finally, prove your fix by confirming the baseline is approved and automatic limits are restored. Passing means the leakage cause has been identified or ruled out objectively. Makeup water returns to the approved baseline. Water chemistry remains within acceptable standards, and system protection along with normal authority is fully restored. On this slide, we focus on handover evidence and operating readiness for the Data Center MVAC system. The service is considered ready only when all technical, procedural, and competency evidence is complete. This includes thorough documentation from the design phase, such as the owner's project requirements, basis of design, calculations, pressure envelope, approved PNIDS, and product data, or any deviations. Moving to installation, we must verify as-built tags, valve lineups, precharge settings, air gaps, drains, and overall inspection and cleanliness. Controls are equally critical, involving point schedules, sequence and alarm settings, sequence of events clocks, BACnet and supervisory control certificates, as well as backups and access controls. Testing and operations processes must be well documented, alongside personnel competence demonstrated through scenario assessments. Finally, a complete searchable handover gate confirms normal lineup is proven. Standby systems are available, spare parts and maintenance are scheduled, and that asset registers, water baselines, and open risk registers are all up to date. This comprehensive approach ensures reliable and safe system handover. In this competency assessment for Module 07 on pressurization, degassing, and water integrity, learners are expected to demonstrate engineering judgment and evidence-based operation, rather than just recalling information. You'll need to explain by drawing the complete PMD, makeup, degassing, and filtration boundaries, and clearly identify pressure and chemistry ownership. You'll be required to calculate key parameters such as static head, top point margin, expansion volume, absolute pressure acceptance, and relief margin. Diagnosing issues is also critical, including recognizing low or high pressure conditions, repeating makeup problems, membrane failure, presence of gas or solids, and deviations in water chemistry. Operating the system correctly, proving your actions, escalating when necessary, stating authority, restoring normal operations, and retaining all evidence are essential steps throughout this process. To pass this standard, you must perform correct calculations, follow a safe sequence, conduct independent pressure proof, position standards accurately, recover from failures, and maintain a complete restoration record. In this module, we focus on the critical standards and reference materials essential for designing and operating data center MVAC systems. Always use the licensed current edition of standards, approved project documents, and precise equipment data to guide final design and operation. Key standards include the Uptime Institute Tier Standard for Availability and Topology, ANSI/TIA, 942C for rated certifications, and ANSI/ASHRA 90.4 to 2025 along with OSHRI TC 9.9 for data center engineering and liquid cooling. For water and pressure practices, important references are EN 12828, VDI 2035, and BSRIA BG 29, plus relevant local codes. The reference hierarchy moves from engineering basis and project requirements, through OEM guarantees and installed testing, to an established operating baseline. It's crucial never to treat owner targets, vendor examples, or draft initiatives as universal standards. Always confirm the adopted edition and jurisdiction before procurement, commissioning, or certification to ensure compliance. Now, let's review the final operating readiness matrix, a crucial step before handover. Each domain must be declared as ready, conditionally ready, or open, ensuring no silent assumptions remain. For the pressure envelope, we need to confirm that cold, warm, top, and relief margins all pass, with failure modes tested and trends synchronized. Expansion capacity must meet pre-charge and retention criteria, verified through calculations and field tests. Makeup systems should be qualified, metered, limited, and autonomous, with passing valve and source loss events logged for review. Degassing processes require successful vacuum cycles, venting, and returns, with fault conditions monitored and cycle records maintained. Solids levels must be within cleanliness and pressure drop targets, with separators and filters serviced regularly and chemistry carefully controlled through lab reports. Control systems must demonstrate local autonomy and secure supervision, supporting network, certificate, and power loss scenarios with comprehensive events and recovery logs. Finally, personnel competence, standard operating procedures, and spare parts inventory must be verified through scenario drills and documented with signed handovers. The release gate ensures all safety and availability critical items pass, with any residual risks managed through approved owners and compensating measures. This thorough process guarantees a reliable and secure MVAC system ready for operation. As we wrap up Module 07 on pressurization, degassing, and water integrity, the key takeaway is to maintain a closed-loop service that can be trusted. Reliable pressure doesn't just happen. It's the visible outcome of managing volume, gas, solids, chemistry, controls, and disciplined operation. To do this effectively, we must engineer the physics by carefully surveying elevation and volume, using absolute pressure, calculating real expansion, protecting top point and relief margins, and distinguishing between facility and technology loops. Next, specifying capability means setting clear project targets with units and conditions, ensuring an OEM guarantee, qualified makeup, measurable results for gas, particles, and chemistry, and implementing local safe control. Finally, proving and preserving the system involves calibrated synchronized tests, handling concurrent maintenance and fault scenarios, restoring normal states, maintaining a metered makeup baseline, and having competent operators supported by indexed evidence. Remember, the design rule combines standards outcome, an engineered envelope, product guarantee, installed proof, and disciplined operation to achieve optimal MVAC system performance.